Hello, and thank you for watching this brief tutorial on the considerations needed when measuring radioactive materials using mass spectrometry. My name is Ben Russell and I work in the Nuclear Metrology Group at the National Physical Laboratory in the UK. As with a number of analytical techniques, mass spectrometry requires routine maintenance to keep it performing at the optimal level and to minimise the extent and impact of contamination that would otherwise limit the applications of the instrument. When it comes to radioactivity measurement, this form of contamination presents an additional consideration for the user, both in terms of the applications of the instrument and from a safety aspect for the user. This tutorial will focus on inductively coupled plasma mass spectrometry, or ICP-MS, as this is the most frequently used mass spectrometric technique for radionuclide measurement. There are a number of other mass spectrometric techniques used for radionuclide measurement, including thermal ionization mass spectrometry or accelerator mass spectrometry. And while some of the things covered in this tutorial will be familiar across techniques, there are going to be specific considerations for different instrument types that need to be considered. Before we move on, it is worth showing the range of applications that there are when using both ICP-MS and other mass spectrometric techniques for radionuclide measurement. The actinides is perhaps where it all began for mass spectrometry, particularly for very long-lived radionuclides like uranium-238 and thorium-232. But as the technique has improved, both in terms of sensitivity and interference removal capability, what are medium-lived radionuclides with half-lives of hundreds or perhaps thousands of years are now increasingly measured using this technique, radionuclides such as strontium-90 or nickel-63. Isotopic ratios are a very powerful technique, both for contributing to half-life measurements through isotope dilution and for source attribution to determine the source of nuclear contamination. For long-lived low abundance radionuclides with a very weak decay signature, mass spectrometry is very well suited to these radionuclides, things like iodine-129 and technetium-99. It can also be used for stable analogues of short-lived radionuclides, such as those in nuclear medicine. When looking to develop and validate separation schemes, you can use stable analogues prior to using active material. You can also use it to characterize things like reference materials or separation resins that have been developed for separating radionuclides prior to measurement, and it is increasingly used in the development of radionuclide standards, where the requirements for end users are slightly different or can be significantly different when it comes to the activity levels and the impurities compared to standards that are developed for use with decay counting techniques. This figure shows a simplified layout of an ICP-MS. This will differ between labs, but hopefully shows the major key components that you expect to find, and we will be referring to this throughout the tutorial. This slide focuses in a little bit more on the key components within the mass spectrometer itself. So we introduce our sample typically in dilute acid, although there are variations to this, and indeed a lot of variations to the sample introduction system. It's a very versatile technique in that respect. The torch, this is the inductively coupled plasma part where the sample is evaporated, atomized and ionized into a beam of singly charged positive ions. The interface then focuses this ion beam as it passes from atmospheric sample introduction to vacuum conditions. The mass analyzer then focuses the ion beam by the mass to charge ratio that the user wants to measure, and the detector most commonly measures the output in counts per second, although there are some different designs in this area. And one advantage of ICP-MS is, regardless of the radionuclide being measured, the time to do a measurement of each sample is several minutes, and it's capable of processing several hundred samples per day, looking at multiple stable and or radioactive isotopes within a single run. Referring back to the earlier diagram, this shows the extract and rotary pump. So that is the extract of argon from the instrument, and the pump that maintains the interface vacuum towards the front end of the instrument. Now, there could be some radioactivity lost in the argon gas extract, and therefore the discharge limits of the lab must be well understood. There is also the potential for the pump oil to be contaminated depending on the activities run and the length of time that is left between oil changes. And therefore, it's very important that the oil is monitored using techniques such as liquid scintillation counting or gamma spectrometry prior to disposal to make sure it's being disposed via the appropriate route. There are options that have been used in some labs to try and limit the contamination. That might be using an additional filter on the oil piping to trap some of the activity, and some have looked at using oil-free pumps to remove this particular source of contamination as well. The autosampler is responsible for moving a probe to the sample pre-selected by the user, and then that sample is pumped into the introduction system of the ICP-MS. In between each sample, it is important that the autosampler probe is washed to minimize the impact of cross-contamination between samples. And this can be done using either a static wash bottle containing a rinsing agent or a recirculating wash that is pumped from a wash bottle into a reservoir that the autosampler probe sits in for a predetermined amount of time. Or it might be that a combination of static and recirculating washes are used. Different reagents can be used depending on the extent of the washing that is needed, for example how sticky an element is in the instrument or the activity levels that are being measured in the samples. For example, you could use as a first rinse stage a more concentrated nitric acid solution, perhaps somewhere around 5%, and then slowly reduce that. So perhaps the next wash stage could be 3% and then finally 1%, which matches the reagent that your samples were prepared in. Either way, it's very important that regular blanks are run between samples to monitor for and correct for contamination. Some laboratories will measure blanks between every sample that they measure. In some cases, the ICP-MS software will be equipped with a feature where the wash will run until a threshold count value is reached for either an interference or the analyte, so that perhaps at the start of the run, when the instrument is relatively clean, the wash time will only have to be, say, 2 to 3 minutes to reach the threshold blank value that is required before moving on to the next sample. Whereas after running tens or perhaps hundreds of samples, it might be that the wash time required to achieve the same level is on the order of 5 or 10 minutes perhaps, but either way it makes sure the instrument reaches that same point. After the autosampler probe, we have the sample introduction system, where the typically aqueous sample is introduced to the inductively coupled plasma in the torch. Now, typically plastic tubing is used for this, and similar tubing is used for removing any material that is not used into the waste. It's good practice to use a dedicated waste bottle for active waste that can then be disposed of via the appropriate waste route. That will depend on the activity of the samples that you are measuring. And as with all ICP-MS applications, the tubing needs to be checked before every run, both for the sample and waste tubing. As soon as it becomes flattened by the pump that holds it in place, or as soon as it visibly starts to lose its elasticity when moved, or if there is any evidence of contamination when using the sample, then that is the point at which it needs to be disposed of. When it comes to the nebulizer and the spray chamber, as mentioned before, there is a lot of flexibility in the instrument design, and that will impact the cleaning approach can be used. So one example is that a glass microconcentric nebulizer could be cleaned in a 5% nitric acid solution for 5 or 10 minutes, but any longer than that and you risk damaging the nebulizer itself, and sonicating it will not be beneficial to it either. But for other nebulizer designs, that might not be the case. After the nebulizer and the spray chamber, the sample goes into the inductively coupled plasma, or ICP, part of the instrument, which is held within the torch, an example of which is shown in the top photograph on the right hand side. The sample will then go from atmospheric to vacuum conditions, and that requires the focusing of the ion beam to the mass analyzer, and that is achieved using the interface cones, which is shown in the lower of the photographs on the right hand side, and then a series of ion lenses. As is the case with the nebulizer and the spray chamber, if there's evidence of contamination in the results that are measured, then these components can be easily removed and can be cleaned using a range of techniques depending on the design. So the torch shown here is a glass torch that can be left in a 5% nitric acid solution for a number of days if required. The interface cones can be cleaned using a range of options, so that might include diluted nitric acid, diluted detergent-based solution, and or some granular powder and sonication between each of these stages. An additional consideration for the interface cones, where the orifice is on the order of only around a millimetre or so, is that for high matrix samples, these can become blocked over time and can become blocked very quickly when running higher matrix samples, such as solid material digests. When it comes to the detector, the treatment of this is similar as it would be for measuring stable isotopes. So cross-calibration of the detector, if it's a dual mode single collector with a pulse and an analog setting, or if it's a multi-collector instrument with multiple detectors in the setup. Calibrating across these is very important, particularly for isotopic ratio measurements in the case of multi-collectors. Either daily or every time the instrument is used, there are a number of factors that can be checked to ensure the detector and indeed the instrument generally is performing as it should be. This is good practice if you, in any case, but perhaps particularly if you run a range of different radionuclides and a range of different sample matrices. It gives you a baseline where you have a standard tuning solution and you make sure that the instrument is performing to a baseline level before you go on to measure this range of unknown samples in your laboratory. So that can include, but is not limited to, the sensitivity over perhaps low, medium and high masses, the uncertainties in those measurements, ensure the peak axis is in line with the mass being measured and that the resolution is sharp enough, the settings on the plasma and the electromagnet that controls the inductively coupled plasma, the lenses that are used to focus the ion beam, and also the settings of the detector itself are all in line. This final slide shows a couple of additional considerations. Firstly, and again this is the same case as if you were to run stable isotope measurements, an internal standard should be added either to each sample or in some cases via a dedicated internal standard line where it's mixed with the sample, because that can account with changes in instrument conditions during a run, and that might be blocking of the cones in the case of high matrix samples, or it could be changes in instrument conditions during a run, such as variations in the plasma gas flow rate. The graphs on the right hand side aim to show that if you don't run an internal standard, you can potentially report quite large differences in the count rate, which might not necessarily be because of the samples, but because of the performance of the instrument. With internal standard, the choice of element is very important. You want it to be close to the mass of the radionuclide being measured, but you don't want it to interfere with that measurement. So something 1 mass unit away might contribute through hydride or tailing interferences, for example. You don't want the internal standard to be present in the sample itself, and it should have an ionization energy that is similar to the radionuclide being measured. With regards to the activity levels being measured, then dilution of the sample might have to be considered, and the extent of sample preparation, so separation of interferences or pre-concentration. That depends on the instrument design. So if you have an instrument with built-in reaction cell, for example, that might assist with the separation of interferences and might reduce the extent of chemical separation that is needed. But with dilution, you have to consider the half-life of the radionuclides of interest. If they're shorter lived, then if you dilute a higher matrix sample, you might do that at the expense of being able to detect the radionuclide. And you also need to factor in the limits of what your laboratory is able to handle. If higher activities are handled routinely, then it is possible to install a glove box around the front end of the instrument, but that obviously has implications for a number of the maintenance steps that have been mentioned in this presentation, and essentially how straightforward those maintenance steps can be and what variations you can make with regards to the sample introduction system. Thank you very much for your attention. I hope that you found this introductory tutorial interesting, and if you have any questions or comments, please do get in touch. Thank you.